So in this video, we will study the kinetic theory of gas. So we will start with pressure. So we know that the pressure is equal to force per unit area, and force can be written as change in momentum per unit time, and this is 1 upon area as it is. So pressure becomes momentum transferred by the molecules of wall per unit time per unit area. So now let's consider a cubical box. So this is a cubical box with the area L square. So the size is L. So this means that area is L square and volume is L cube. And box contain N molecules, so there are plenty molecules. So the velocity of the molecule number 1 is V1, which can be written as V1x, V1y, V1z. So this is the velocity vector. Now we will consider a single molecule with mass m, which is moving along the x-axis with the velocity v1x. So suppose that this is the left face of the cube, this is the right face, and molecule starts from this and it travels along x-axis with the velocity v1x. And when it reaches the right face, it collides elastically and then rebound with the same velocity. So we can write the initial momentum as mass times the velocity, and the final momentum is negative times mass times velocity, and hence the change in the momentum becomes negative 2 times m times v1x. Now, as I said, that molecule starts from the left face, and so the molecule starts from the left face and it reaches the right face, and the distance that it covered is small l. And then after colliding, it then comes back to the left face, covering the same distance l. So what is the time taken by this molecule? So the velocity is v1x and the distance covered is 2 times L. So the time would be distance upon velocity. So this is the time. Now, when molecule starts from the left face, it hits the right face. So let's calculate the force that the face of the cube apply on the molecule. So according to the Newton's second law, force is just the rate of change of momentum. We have already calculated the change in momentum, which is negative 2 times mass times velocity, and this is delta t, which we already calculated. So we just substitute delta t, which is 2l upon the velocity, and upon solving we get negative mass times velocity square divided by l. And remember that this is the force which is applied by the phase on the molecule. Then, according to the Newton's third law, the force that molecule applies would be equal in magnitude and opposite in direction. So the negative sign will be replaced by positive sign. But this is the force by just one molecule. But we need to calculate the force that each molecule exert on the face, on the right face, this one. So we will sum the forces that each molecule exert on the face. So it will be mass times v1x square upon L plus, sorry, this is v2 plus v2 plus v3 and so on until vn. And then we will factor out m upon L, and we will be left with the sum of the square of velocities. Then we will divide both sides by L square. So this will become force divided by L square. And remember that this L square is the area and this L cube is the volume. Now, remember that the mass of one molecule is small m, but we have n molecules and mass is quantized. So we will just multiply capital N with m to calculate the total mass of the molecules. And according to the definition of density, which is the total mass upon total volume. Total mass is capital N times m. Total volume is L cube. So calculating for mass upon L cube is just equal to rho upon capital M. So remember we divided L square on both sides of this equation, this one. So we will just substitute rho upon M in place of M upon L cube, and then we will shift N underneath the sum of the square of velocities. So this is nothing but the average of square of velocities. So we have n molecules. Each molecule has a velocity v1x, v2x, and all the way up to vnx. And if we divide it by total number of molecules, we get the average. So this was the pressure in x direction. If we do the same calculation in z direction and in this direction, so we will get the pressure in y and z direction, which will have the terms vy square and vz square. But according to the Pascal's law, pressure is exerted equally in all directions. It means that the pressure in x, y, and z directions are equal. So the rho will cancel and we will be left with Vx square. The average value of Vx square will be equal to the average value of Vy and Vz square. And according to the vector addition, so suppose that this is the velocity vector, this is z, this is y, and this is x axis. So this velocity has three component, Vx, Vy, Vz. And if I calculate the magnitude square of the velocity, it will be nothing but Vx square plus Vy square plus Vz square. And if I just average these velocity, so it will give me this relation. But according to this relation, all of these quantities are equal to each other. It means that this v square, the averaged v square, is equal to 3 times average of Vx square. So I can calculate Vx square, which is equal to 1 upon 3. So this 3 will come on the left hand side and will become the denominator. So Vx square is nothing, just it's V square divided by 3. And remember that my pressure was rho Vx square, and Vx square was nothing, it was 1 upon 3 V square. So I just substitute Vx into the equation for pressure. And now remember that the density was total mass upon total volume. Then I would just multiply and divide this equation by 2. I will put my mass into the average because it's constant. So the average of mass is nothing but the mass itself. And I get a nice relation which relates pressure with the average value of kinetic energy, and N naught is the number of molecules per unit volume. So this relation tells us that the pressure is directly proportional to the average kinetic energy of the gas molecules. Now we will interpret the temperature in terms of the kinetic theory. So let's start with the ideal gas law, which states that PV equals nRT, where n is the number of moles, or is the ideal gas constant, and recall the relation between the moles and molecules. The number of moles is total number of molecules divided by the Avogadro number. So I will just substitute this relation into this equation, and I get this result. And remember that ideal gas constant divided by Avogadro number, it gives me Boltzmann constant. And we already derived the pressure in terms of kinetic energy, which is nothing but 2 upon 3 number of molecules per unit volume times the average value of kinetic energy. So I have this relation and I have this relation, so I just equate them. So upon equating, I get n kBT upon V equals to 2n divided by 3V times average value of kinetic energy. So n would cancel, V would cancel, and the average value of kinetic energy becomes equal to 3 by 2 kBT, which means that the average value of kinetic energy is directly proportional to the temperature. If I increase the temperature of gas, the average value of the kinetic energy also increases proportionally. Now let's calculate the kinetic energy of 1 mole of gas. So remember that the molecule, one molecule has mass m, and if I have Avogadro number of molecules, so it will have mass capital M, like the mass of 1 mole, which is often called the molar mass. So we know that the mass is equal to the molar mass upon Avogadro number. So we already calculated the average value of kinetic energy, which is 3 kBT upon 2. So I will substitute kinetic energy, which is half mv square, and then mass equals to the molar mass divided by the Avogadro number. So I will just substitute it here. And then I will move this Avogadro number to the right hand side. And remember that R upon NA was equal to the Boltzmann constant. So if I move it here, so KB times Avogadro number becomes equal to R. So this thing becomes equal to R. And this two, let's not cancel this one. So half capital mv square becomes equal to 3RT upon 2. So this is the average kinetic energy of the ideal gas of 1 mole. Now recall that pressure was rho upon 3, the average value of velocity square, and uh, we can isolate v square, which is equal to 3 capital P upon rho, and when we take the square root on both sides, we get this relation, and the square root of the average velocity. So average velocity square is nothing but root mean square. So root mean, so root means square. So root means root and mean is the average and square of. So this is the root mean square, and so we express the root means square speed in terms of pressure, and we can express this in terms of the kinetic energy or the temperature. So recall that 1 upon half mv square is just 3 kVt upon 2. So this 2 and this 2 would cancel with each other. This m will come to the right hand side, and when we take the square root, we get this one, and this is nothing but V RMS. And this kVt upon m, kVt upon m, kVt is nothing but uh, so R upon Na was kb. So kb is mm, kb is R upon Na times m, and this Na times capital M, so it's 3RT upon m, where m is the molar mass. So this is all with the kinetic theory of gas. We started with the pressure, then relate it with the kinetic energy, and we also relate the temperature with the kinetic energy. Then we move to root mean square speed and relate it with the kinetic energy, which is also a function of temperature and pressure. And at constant temperature, it is important to note that the root mean square speed is inversely proportional to the square root of molar mass. So this is an important result. So if the molecule is heavier, so for example, the root mean square speed of the hydrogen will be greater than that of oxygen. So that's it for today. Thank you.